Hi everyone. Today we're going to be talking about these things called vector projections. So I don't know if you've ever seen this very silly clip of Professor Leonard. If you've taken Calc 3, you may have seen his videos. I'll play the clip now.
Orthogonal vectors here. Do you know that I have a dog? I hate that dog. He's a great dog, but oh my gosh. Every time, we don't go on walks, we go on drags. Because it's me dragging him everywhere. Because he likes to sniff and poop. I don't know what's wrong with this dog, but he poops like 13 times a day. It sucks. I've worn out like 4 shovels, all right? That's saying something. So here's my problem, all right?
But yeah, so Professor Leonard is a crazy funny guy, but something that I struggled with in Calc 3 is understanding a projection itself. So those of you that are not familiar, if we have some vector u in space, that vector u is comprised of a u of x component and a u of y component. But let's say for the sake of this example, because not all the time will we be on the x and the y axis, we'll call this x1 and x2 respectively. So where u is equal to the summation of the 2 individual vectors. Okay? But let's say that we have some other vector which is parallel to u1. And let's call this vector a. So it's going in the same direction as u1, and it has some angle theta between u and a. And notice that u2 thus is orthogonal to said vector. So there's something we can do to find each of the vectors. And what a projection of u onto a does, so if you've probably seen this notation before, a projection of a onto u, that is simply going to find how much of the u vector is attributed to a. That's the way you can think about it. Basically, it's finding the component that is parallel to A. That's a projection. And you may have just been given a formula, and the formula looks like this. So simply put, it's the dot product of U and A over the magnitude of A squared, and that's a scalar, right? So this is a scalar. And then we times that, or we do scalar multiplication of the vector A, which is this guy here, which I'll rewrite to be as such. Okay, so let's actually prove the projection formula, because this is like, well, why? Why? Where is this coming from? Because if you just were handed this in Calculus 3, like I was, you're probably like, well, this is really confusing. So let's go ahead. It starts with the simple fundamental idea that u1 is a scalar multiple of a. So u1 is equal to some scalar k times the vector a. All right, so, and that makes sense, right? U is only a fraction of a. All right. Okay, but then recall this formula too. So we have these two ideas. Let's simply just substitute u1 in. So u is equal to ka, scalar k times vector a plus u2 in that vector. Remember, u2 is this guy here. Okay, now what we'll do, we have to pull out a theorem that we know. We know that the dot product between u and a is equal to, and this is a defined theorem that we're not going to prove, is equal to, u1 plus u2 dotted with a. All right, and that should make sense, because all we're doing here is we're taking the u. This part is known, but the other part is not so familiar. The next part we'll see. This should make sense. U is defined as the addition of these vectors, right? If I take u, add it to u2, we get just the u vector. So I'm just expanding that, and I'm adding the a part to it, we're just dotting together, right? Because we know this to be true. That's pretty obvious. I always hated math proofs when they're like, if you didn't huff glue in kindergarten or if you didn't eat crayons when you were a child, then this is true. That's how it feels sometimes. But you should be able to see this, right? Because this is just simply expanded. So sorry that I misspoke there. Okay, this is where that unfamiliar theorem comes from. U dot A is equal to simply A U1, right? And this will be, sorry, I'm blanking. This is gonna be a dot product between these, and then A and U2. All right, and these are dotted together. All right, but we've already defined U1, so let me see how much room I have here. I'm gonna go ahead and erase this part and rewrite it over here. So U equals U1 plus U2. All right. So now what we're going to do here is substitute in U1 for the Ka bits. So vector U dot vector A is equal to, and that's going to be Ka dot A, and that's going to be plus A dot U2, okay? And we're about done here, but we have to figure out just one more little thing. Let's consider this dot product here. A, sorry, I should be writing my vector notation. A here is this vector, and U2 is this vector. Well, if you remember, cosine of theta is equal to A dot U. If we consider the dot product between A and U2, that's going to be over their magnitudes, right? And if we consider what this dot product is equal to, well, the angle between A1 and A2, well, that's simply 90 degrees. Cosine of 90 is 0. So this whole thing goes to 0 where the dot product is equal to 0. So keep that in mind. And that will help us make a simplification right here where this is 0, okay? But let's also consider this guy here. So we said this was 0, so that's out of the equation. So now it's U dot A, right, equals Ka dot A. Well, what do we know about A dot A, or any vector dotted with itself? Well, hopefully you remember that A dot A is equal to the magnitude of that vector squared. And just a little proof, because it's really easy. Let's say that A is A1 plus A2, or sorry, A1, it's just this vector, all right? So the dot product between them would be this dot that. So it would be A1 squared plus A2 squared. And if we take the magnitude squared, well, we know that the magnitude is simply this, right? A1 plus A2 squared, but we're squaring it, so that's squared, and we see that these are thus equal, right? Because A1 squared plus A2 squared is equal to square of the square root of those constituents that we've seen. All right, so we're going to make a little bit of a simplification here. Instead of A dot A, let's just simplify the dot product to the magnitude of A squared. All right? Pretty simple so far. I don't think this is too hard to see. But how do we get to the projection? Well, if we recall, the projection is U1. So let's go back to the formula that U overall is equal to U1 plus U2. All right? Okay, sorry, I was blanking a little bit. u1, in this case, we recall being Ka. All right, but now we know what K is because if we divide out the magnitude, K is equal to the dot product over the magnitude squared. So U is really just going to become equal to sorry, not K, we're literally defining that, U dot A, and that's going to be over the magnitude squared, and that's going to be dotted with A, all right, or multiplied, sorry, because this is a scalar. Very important, this is a scalar. That's equal to U2. Well, this actually finds the reverse projection because what this is saying is that U2 is equal to the vector U minus whatever we found projected, which was U1, and when we do that, we get U2. So simply put, U2 is equal to the vector U minus this vector, right? So the best way to think about it is we take, if I can get some space here, that'd be great. We know that, let me just erase that a little more. If we have the vector U and we go back U1, so this would be U minus U1, right? Well then, if we add tip to tail, we get U2, right? Because U2 is parallel and equal in its magnitude here. So hopefully you can see the similarity. And that's equal to U2. Well, simply put then, what is U1 equal to? Well, and that's what we define the projection to be. So this is the projection of A onto U if the orthogonal way. All right, so U1, simply put, is just this, okay? So if we want to know what the actual projection is here, right, this projection, well, that's simply just now U1, because if U2 is the vector of the projection this way, well then this vector here is the projection in the non-orthogonal way. Simply put, U1 is equal to, U1 is the projection of A onto U, of U onto A, and that is just going to be equal to this bit here. So the dot product, U dot A over the magnitude squared, that's a scalar, and then add or multiply that scalar to your vector. So that's the proof for projection. Sorry, I was a little rough there, but that in essence is vector projection. And hopefully I did a good job proving it. Basically we worked backwards. We said, okay, this is true, blah, 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 theorem, blah, blah, blah. We have the vector U. If we make a component on this A version here, well, we have an orthogonal bit. Let's find that orthogonal bit. That's what we're finding with the U2 of the projection of A onto U orthogonally. And then we just extrapolate using our common sense, saying that U1 thus is, if U2 describes the projection in the y direction, well then U1 describes the projection on the x axis, or along A, I should say, not on the x axis, but simplifying it in my head a little bit. But yeah, all right, that's going to be it, guys. Big smiley face if you've understood that, and have a wonderful day. Bye-bye.